Okay, we're going to wrap up here chapter 12. We pretty much finished the main part of chapter 12, which was equilibrium calculations. Last time we did a number of ice table sort of calculations. Again, initial concentrations, changes, which usually represents by x's. Remember, again, as we talked about, you do need to make sure you use the coefficients if there is any in the balance equation. That way, again, you do get the right mole-to-mole relationship. That'll get you your molarity minus x, and x. Remember, this goes into your equilibrium expression. And then you can solve for x. X again will basically be the change part here. And that will allow you to get to the equilibrium concentrations. Everybody remember, as well as we talked about, you could do it with pressures. So again, it does need to be atmospheres. If you are going to do it with pressures, I think our very last one was in atmospheres there. We basically talked about three different ways that you could solve this. Again, you could have like a perfect square situation, maybe on both sides. You could quadratic it. And the last way we talked about is you can make an assumption and assume x is equal to 0. Remember that we can only really do the assumption if our k value is small. And that is the only time that we should try the assumption. Again, the idea there is if our k value is small, the change part is not going to be all that big. It's mainly going to stay on the reactant side, so we can't assume x is going to be 0. Remember that essentially, for example, here, it is all the x's except the one that started at 0. So we do not obviously get rid of all the x's, otherwise we have nothing to solve for. Also, remember, if you do make the assumption, you do need to check it with the 50% rule, now the 5% rule. And basically, the way that we check our assumption is we take our x value that we got, we divide it by, really, in most cases, the initial concentration or pressure, and we times it by 100%. Once again, if it's 5% or less there, then you should be good. If it's greater than 5%, then you really do need to go back and sort of solve it another way. In most cases, that would then take you probably back to the quadratic. You can also, as we talked about, if you don't want to even bother with the assumption you like to in the quadratic, you could just always do the quadratic. It will work, and you could go that approach as well. Any questions on any of that there? All right, last thing we're going to talk about in this chapter is what is known as Le Chatelier's principle. And Le Chatelier's principle is the idea of we have a system that is at equilibrium. So we have this guy here that is at equilibrium. And again, a reminder, as we've been talking about, the rate of the forward direction will equal the rate of the reverse direction in that situation. And basically, what happens in sort of Le Chatelier's principle is this. You basically do something to screw up the equilibrium. So you add what is sometimes referred to as a stress to the system. And what that's going to do is basically mess up the equilibrium. So you'll mess up the equilibrium. But as I mentioned before, really kind of, if you think about it, the goal of these type of reactions is always to kind of get to equilibrium or get itself back to equilibrium. So what will happen in a situation like this is if you have a system that's in equilibrium, you do something to it to really mess it up, it's going to cause the reaction to basically do really one of three things. It may shift to the right, which means it would need to make more products. It may shift to the left, which means it would need to make more reactants. And then there are certain situations that no matter sort of what you did, even though you kind of did something to it, it will actually cause a no change to occur or no really shifting occurring in that situation. So those are really the kind of the three options you typically come across when you're dealing with Le Chatelier's principle. Shift to the right, shift to the left, or not much happening in that situation. So what is a stress that will cause this to happen? Some common stresses here is you could do something to concentration. You could do something to pressure and volume if you're dealing with gases. You could do something to the temperature. You could add something like a catalyst. And these are, again, basically all things that you could do to a system that's at equilibrium that can sort of mess it up and, again, cause the shifting to occur. The goal for this is essentially you're at equilibrium, you do something to mess it up, it gets itself back to equilibrium a second time. So that's sort of what the shifting is going to allow it to do to get itself back to that rated forward direction will equal the rated reverse direction. So we're going to talk about each of these and sort of what's happening and what the effect on sort of the equilibrium is. So let's get going with this idea of concentration. And when we talk about concentration, there's basically two things that you could do with concentration. You could either add more or you basically can remove. And those are really your kind of two options with concentration. When we add more, what happens is it will shift away from the side you added it to. So what do we mean by side? We're really talking about the balance equation. So when you look at the equation, reactants or products, that's sort of what we're talking about in terms of side. Obviously, if I have this equation happening and I had everybody there in the beaker, there really is no like left side or right side of the beaker. Everybody is floating around basically in that beaker together. So when we talk about kind of like, right side, left side, we are talking about the balance equation and sort of what's on each of those sort of sides of the equation. So if you add more, it will shift away. So AA is a good way to remember that. Add away, it will happen. If you remove something, it will actually shift towards the side you removed. So if you add something, it'll go away from it. If you remove something, it will come towards it. You could think of it like, when you remove something, you make like a big old hole on that side and it needs to kind of fill it. And that is a way to kind of remember it. Now, adding more is pretty simple. If you want to add something, essentially in most cases, you could go to the reagent shelf, grab a bottle that has something in it, for example, like iron 3 nitrate. If you want to add some iron 3 to your equilibrium, you grab the iron 3 nitrate. That's a source of iron 3 and nitrate, and you could just add that in. And obviously, it'd be like adding more iron, obviously, to that equilibrium, to the beaker. Um, if you want to remove something, especially from a say solution, what we really have when we have a solution, right, is we have ions floating around basically in the liquid part there of the solution. And if I wanted to remove an ion, for example, from this equilibrium, I really can't just reach in there and grab it out. Not a great idea, right? So you don't want to do that. But I do need to kind of get it away from there or out of there. So there's a couple of ways that we could kind of remove something from an equilibrium solution. One very common way is I could add something to this that will maybe react with something that's there and cause a solid or a precipitate to form, right? And when it does so, making that precipitate, which is a solid and as we know, not included in the equilibrium expression, that's essentially like reaching in there and just taking out that ion from the solution. So that's a very common way we could remove something from solution is to add another reagent to it that will precipitate out something that's floating around. So for example, if you had chloride ions floating around in that solution and you want to remove the chloride ions, you could grab something like silver nitrate, and that is a source of silver and nitrate, which is perhaps not an equilibrium reaction. But silver, when it's added to a solution that contains chloride, based on solubility rules that you might remember, silver and chloride will come together to make silver chloride, that white sort of solid you probably made in one of those reactions in 200A, or a number of them along the way. And again, that would be essentially like removing chloride, for example, from that solution. And that's something you could visually see. There is also another way that we could kind of remove something from a solution. So for example, let's just say we had some hydroxide ions basically floating around in a solution, or maybe you had some H plus ions floating around in the solution. But here we have hydroxide. So if I take an acid, which is basically a source of H plus, which you might remember from naming acids, the cation is H plus basically. And when you do that and you add that to this solution, H plus and OH minus will come together to make water, which you may not visually be able to actually see you did that. But that would essentially be like removing hydroxide from that solution, right? As water is a pure liquid, also not included in equilibrium expression. And again, that would be like pulling out. You also could do a similar thing if you had a solution that had H plus in there, right? Or H3O plus. You could add a base to it like hydroxide, and you would make water as well, and you can remove it. So removing is usually made or done in a solution like this by either making, say, precipitate, or adding something that, for example, if you have hydroxide or H plus, that you can make water to remove it. Any questions on that there? Now, a way to think about this is like so. So let's just say we had seesaw here, and we had this stick figure over here. This is advanced stick figures. They have faces. That's good. So that is the reactant side. We'll say this side is our product side in this case. And we'll say that this situation here is at equilibrium. So let's just say, for example, that somebody decided to hop on over here on the product side. When we do that, what's going to happen is this situation. And obviously we kind of screwed up the equilibrium there, right? So in this case, what we would need to do is add more people to the left or more people to the right here to kind of balance it back out. Yeah, we would have to go here to the left. So we added to the right. It has to shift away from the side we added it to and go to the left there. And that's going to allow this reaction here to basically restore itself back to equilibrium, if you will. Happy campers everywhere here. And we'll be back to equilibrium position number 2, let's say number 1. Now, if we had kind of the same situation here to begin with, and we had again our system here at equilibrium, and again, we call this side the reactant side, this side the product side. Let's say in this case, though, this guy decided I've had enough. I'm going to hop off in this case. And when he does so, this is going to be the result of that here. Not so good. Again, here to balance it out, we would need more people here now to go on the right-hand side, right? So we actually are going to go towards the side we removed it from. And in that case, that will again kind of return us back to equilibrium in this case. And everybody will be happier, perhaps, in this case here. So if we add more reactants, it will shift away from the reactants, go to the product side. If we add more products, it will go to the reactant side. If you remove products, it will go towards product side. And if you remove reactants, it will go towards the reactant side. Any questions on that there? What is really happening in each of these situations is basically what we kind of talked about at the beginning of this chapter, which is, for example, when we add more products in my example here, there's a lot more products at this point than reactants, which means if you think about our reversible reaction, that should kick off the reverse reaction occurring, right? Because you got a lot more products than you do reactants. They're going to find each other easier, going to cause a reverse reaction to basically take place. What's happening over here? Well, again, similar situation. We now have more reactants than we have products in this case, which means they're going to kick off that forward direction, right? Cause a forward reaction basically to occur. So this really has a lot to do with what we talked about kind of at the beginning of the chapter, the availability of your reactants or products in this case, causing either the forward direction to occur or the reverse direction of this reaction to occur. Or again, if you want to keep it simple, just add away, and you need to go fill the hole when you remove something, right? To always go towards it to kind of fill the hole. Any questions on that there? All right, the next thing we're going to talk about is what will happen when we deal with pressure and volume. And they oftentimes are sort of tied together. And as you remember from 200A and your wonderful gas experience, we had our friend Boyle, right? And he had a law. And the relationship with Boyle's law is as the pressure goes up, what typically happens to the volume? It goes down, right? Opposite relationship, right? And as the pressure, right, as pressure goes down, the volume will go up. The idea there is, right, with a much smaller volume, gas molecules are closer to each other. A lot more collisions going to occur with the container. It can cause a lot more pressure. In a larger volume, everybody has a lot more room to fly around in, right? Less collisions, pressure starts to drop. And when you're dealing with that in an equilibrium situation, if you increase the pressure, you will see a decrease in the volume. So what's happening in this case is essentially the pressure is rising. So we kind of want to bring it back down, because it went up. So we kind of want to bring it back down a little bit. And obviously, if I have a much smaller volume in this case, would I need more or less gas molecules to bring the pressure back down? I would need less, right? So we would need less gas molecules to fill this small volume. That would bring our pressure back down. So what happens in this case is it will shift to the side with the least number of gas molecules. And that obviously is reaction dependent. You have to actually look at the equation and see how many gas molecules you have on each side of the arrow. You should also not overcomplicate that either. You're just looking for everybody with G's and adding up the coefficients, yeah? And that'll tell you how many gas molecules you have basically on each side. Opposite is true here. If our pressure goes down, our volume is going to go up. So now we have a much larger volume. And again, the change that's sort of happening here is the pressure is dropping. So we want to bring the pressure sort of back up. So in this larger volume, we would need more gas molecules basically to fly around. So it would shift to the side with more gas molecules. And again, that is obviously, like I mentioned a second ago, reaction depending as to which way that is. I personally, when I'm thinking about sort of pressure and volume and trying to figure out what's going on there, I usually think of it in terms of volume, and it just matches the volume. So if you have a small volume, less gas molecules. You have a larger volume, more gas molecules. So again, that's a good way to kind of remember it. It matches the volume in this situation. Small, less, larger volume, more. So if I had something like this, so what will happen? Will it shift to the left? Will it shift to the right? Or will there be no change if I add more C, I remove B, I increase the pressure, I add A, and I increase the volume? So take a moment for each of those and decide which way we would expect the equilibrium to shift in this case. Add more C, increase pressure, increase volume, remove B, and add A. Okay, so let's take a look. So we have this system at equilibrium. In this case, I'm going to add more C. So really what you want to think about is C is over here on our product side. So when I add, it goes away. So I add it to the right-hand side, should cause the equilibrium to shift to the left, away from that side. Again, the reasoning here is what we just talked about. We will now have more products than reactants, and that's going to kick the reverse reaction basically off to occur. If I remove B, B's over here on the reactant side. So again, I'm going to basically make a hole over there on the reactant side that I need to fill. So it will also cause it to shift to the left. Again, the real reason is the same reasoning. By removing those reactants, again, now we have more products than reactants, going to cause the reverse reaction basically to occur in this case. Now, question on those two there. If I increase the pressure, again, I'm going to think about it maybe in terms of volume. If I increase the pressure, that means my volume is going to decrease. So remember, small volume, less gas molecules is what we need. Again, that's because our pressure is increasing. We kind of want to bring it back down. So we need less gas molecules to do that. These are all gas molecules. That is 2 and that is 1. So there are 3 gas molecules there. That is a 4. There are 4 gas molecules here. So in this case, we will actually shift to the left as well in this example. Here I'm adding A. A is over here on our reactant side. That's going to add away from it, which would cause it to go to the right in this case. Again, the reason here really is by adding more A, again, more reactants than products going to cause the forward direction basically of this reaction to occur. And we'll go that way. Lastly here, increasing the volume will really drop my pressure. And what we want to do is kind of bring the pressure back up. So now we have a larger volume. So again, volume matches, right? So large volume, more gas molecules. And in this case, we would shift there to the right. Any questions on any of that there? Okay. The next things that can affect Le Chatelier's principle is temperature. So as we've talked about previously, temperature is the one thing that also affects the value of the equilibrium constant, as we talked about. And temperature really works the same as concentration. So temperature works the same as concentration. And that means that if you increase the temperature, it will shift away. And if you decrease the temperature, it will shift towards it. Now, how do you know sort of where temperature is? Is it a reactant or is it a product? And what helps you determine that is essentially what type of reaction you're dealing with, whether it is a exothermic reaction or an endothermic reaction. And in a exothermic reaction, heat and energy is released. So in an exothermic, heat and energy is released. And because of that, we consider, it's not correct in all aspects, but we kind of consider heat and energy to be a product in that case. So if it's an exothermic reaction, we think of heat and energy, or if you want to think about it, temperature, if you will, as being a product in that case. And that would mean in an exothermic reaction, if you increase the temperature, it should shift to the left. And if you decrease the temperature, take all your test tubes, throw it on ice, it should shift to the right. That would be like removing temperature in this case. Now, in an endothermic reaction, that is when heat and energy is absorbed. And because of that, we consider heat and energy to be a reactant in an endothermic reaction. So we think of it as a reactant. So it is really the opposite here in terms of endothermic. If you increase in an endothermic reaction, you would expect it to go to the right. And if you cool everybody down there and remove energy or temperature, you would go to the left. So It's important to know, is it exothermic or endothermic? How is that usually displayed to you in most cases? Well, because when they wrote your book, they probably assumed you did that chapter on energy earlier on that they didn't do in 200A anymore, but we will do it. They usually use the delta H, which is the change in enthalpy. The change in enthalpy is basically the heat of a reaction and is calculated by taking products minus reactants. And basically, that is how you typically will see, is it an exothermic reaction or endothermic reaction sort of given to you. They will give you the equation. At the end of the equation, they'll just give you a delta H value. And if that value is negative, that means the reaction is exothermic. And if the delta H value is positive, it really doesn't matter in this application what the number is. It's actually the sign that's the most important thing. Is it positive or is it negative? It will be an endothermic reaction. And again, I would say that is most commonly how you would be given sort of, is it exothermic or endothermic, by be given the delta H value. Most of the time at this level of chemistry, they don't really write heat or energy a lot of times in the equation or anything like that. They're just at the end, give you that delta H value, and that's most likely how you would recognize it. Any questions on that there? The last thing that perhaps can affect the equilibrium is a catalyst, and a catalyst is not a reactant. It is not a product, and it does not get used up in the reaction. It is there in most cases to facilitate the reaction occurring faster. And I would say probably 99% of the time somebody's asking you, you're talking about a catalyst, that's probably what you're talking about, is speeding up the chemical reaction. There are catalysts that actually slow down a reaction, but in most cases that's usually speeding up is kind of the deal there. It doesn't get used up. It doesn't get kind of consumed in reactions. There to facilitate the reaction occurring kind of faster. Questions? No. So for example, a lot of times catalysts, for example, oftentimes are written on top of the arrow. So for example, you may see something like PG, platinum written. You may see something like H plus, which means it's an acid being used as a catalyst. So the idea of what a catalyst can do is there is, and we'll talk about when we go back to that chapter you skipped in 200A, there's what is referred to as an energy diagram. And say this is your reactants, this is your products, this is energy, and the reaction is sort of occurring in that direction. So what happens is as the reactants go to products, basically they have to break all their bonds and make new bonds to make all of the products on their side. So there's this hill here that the reactants has to climb to get to the other side. That's what's known as the activation energy. And it's sometimes abbreviated as E of A. And that's the hill that these reactants have to kind of climb to get to the other side. And the size of that hill determines, for example, how fast or slow the reaction occurs. If that hill is really big, you're probably going to have a lot less reactants that have enough energy to get up and over that hill to the other side. The result of that is probably a much slower reaction than if that hill is much smaller, right? Just like if you were walking a hill and you had a big giant hill to get to the other side of campus, right? It's going to take you a lot longer to get there than if you had something like a speed bump in the parking lot, right? You could just get up and over right to the other side is much quicker, and most people could get up and over a lot quicker to do so. And what a catalyst does is it finds a more, I guess the best way to put it is kind of a more efficient way to get to the other side of that hill. And that could be something as simple, for example, as say a metal catalyst. So let's just say you had gas molecules that were flying around, and these gas molecules eventually need to hit each other for a reaction to occur, right? And without the catalyst being there, they just got to kind of fly around until that sort of occurs. And they have to actually hit each other with the right amount of energy, which is the activation energy, to make that reaction occur. So if you add something like a solid catalyst there, what that can do is these gas molecules may be attracted towards that metal, right? Or that solid. And that's going to bring everybody now much closer to each other and going to allow them to start reacting a lot quicker than it would if they were just kind of flying around and hoping for the best, to find each other. And that's what sort of finds a more efficient way for that reaction to occur. Ultimately, what that does is when you have a catalyst involved, it actually will lower this activation energy. So instead of having to climb, say, the blue hill there, the reactants only got to climb like the red hill, right? And now you can see it's much smaller in energy because it's much more efficient pathway. And now you're going to get a lot more reactant molecules that have enough energy to actually get over that smaller hill. The result of that is typically you see the reaction occur a lot faster. The rate would increase as a result of that. So a lot of times that's sort of what a catalyst does. Something like an acid or a base puts things sometimes in the right pH range for it to be more optimal for things to react and protonate things or deprotonate things. And that allows, again, for things to be kind of in the right sort of way for it to react a lot quicker. Now, what a catalyst does is speed up the reaction. But in the case of Le Chatelier's principle, it actually will cause a no change situation. You'll just kind of get there quicker, but it really won't cause it to sort of move one way or the other. So that's one way that you could get a no change. The other two common ways that you sometimes can get a no change is if, for example, you had a gas situation and you added a noble gas, right? Somebody from group 8. Noble gases are chemically inert, which means they're not going to react, right, with anybody. So that's another situation can have a no change. Another way you could get a no change is what we were just talking about with gases and pressures. So for example, let's just say you had 2 gas molecules on the left and 2 on the right, and you change the volume. And let's just say you need to go to the least number of gas molecules. In this case, which side is the least? Neither. There's the push, right? They're both 2. So this is another place where you could get a no change situation. There really is no kind of more or less. It will just kind of remain the same. So no change is a viable answer for Le Chatelier's principle. And those are the 3 sort of common ways that you sometimes can get it. Noble gas, kind of equal number of gas molecules. Are you at a catalyst? Any questions on that there?
So when you see a catalyst,
In the Le Chatelier's principle question of what's going to happen, no change would be pretty much the safe answer there on that one. Yeah, there really is, stuff happening. It's just that nothing doesn't happen. But in terms of kind of shifting one way or the other, it's going to be a no change. All right. So this is some of the stuff obviously we talked about here a second ago. Concentration shifts away from added, shifts towards removing. Again, temperature is important to know. Is it exothermic or endothermic as to which way it will shift? And obviously pressure, as we talked about, has to do a lot with the volume, is a good way to remember that. So let's take a look at some examples here. So why don't you give this one a go? For each of these changes, will it go to the left, will it shift to the right, or will there be no change in each of these situations here? And for the sake of this example here, we'll just say delta H in this case is a negative number. Here first, we're going to add some H2. So H2 is over here on the left. When we add, it will go away from the side. So we add it to the left, should shift it to the right in this case. Here we're going to remove some NH3. NH3 is over here on the right. So again, when we remove, again, if you want to think about it this way, it's like putting a hole on that side. So we need to go fill that hole, which means it should shift towards it. Again, in this case, we'll have more reactants than products, so causing the forward direction of this reaction basically to occur. We're going to add some N2. Adding N2 means that we're going to go away from it, which will shift it to the right. Again, we're going to have more reactants and products causing the forward reaction to occur. We're going to lower the temperature. So temperature has to do with exothermic or endothermic. So here with the delta H value that's negative, that should tell me it is exothermic in this case. That means in the case of Le Chatelier's principle, we should think of it as a product, right? So it does work the same as concentration. So if we're lowering the temperature, That would be like removing our product. And again, it should come towards the side we removed it at, and it would also shift to the right here. It's very popular on the right here today, I think. We're going to increase the volume, which would technically cause our pressure to go down. Because that's a larger volume, we do need more gas molecules in this case to fix that. Here we have one gas molecule. Here we have 3 gas molecules. That's a total of 4 on the left. Here we have 2 gas molecules. So in this case, we would need to head to the left in this case. Again, to fill that larger volume with more gas molecules, going to cause more collisions, going to bring the pressure back up from it decreasing. Obviously, here in the last one here, we're increasing the pressure, which means our volume is actually going to come down. And because of that, again, small volume means less gas molecules. So since we just did it, right-hand side there has the least gas molecules. Any questions on any of those there? So really, as you hopefully can be seeing, Le Chatelier's principle is really about whatever you did, is it going to cause kind of the forward direction to occur or really the reverse direction of that reaction to occur? All right, let's take a look at a couple more here just to finish it out on. That's the same one. Let's see this one. Oops. All right, let's what's going to happen? Same thing here. We're going to go to the left, we're going to go to the right, or no change if we do the following. Let us add O2, let us decrease the pressure, let us add a catalyst, let us increase the temperature, let us add some NO, let us remove some O2. That was good. Let's give those a go. Okay, so let's take a look. We're going to add some O2. So O2 over here on the left. So that's going to give us more reactants and products and go away, cause that forward direction to occur in this case. Here we're going to lower the pressure, which we know volume is tied to that. So that means my volume is going to increase. And as we talked about, basically volume increasing means large volume, more gas molecules in this case. This side here has 2 gas molecules, 1 of each. Over here has 2 gas molecules. That to me seems like a no change in this case, as it's equal in this case. Here we're going to add a catalyst, and as we also talked about, that is going to cause a no change in this situation. Here we're going to increase the temperature. Since this is endothermic, the delta H value would be positive if we saw it, and that would mean that heat and energy is considered a reactant in this case. So now I'm increasing a reactant, which will cause the forward direction to occur away from it, and we should head to our right-hand side there. And here I'm going to add some NO, which is our product side, going to cause the reversed reaction to occur as we have more products than reactants. And lastly, we're going to remove some O2. That's going to cause a hole on that side. And again, can cause more products than reactants, can cause the reverse reaction basically to occur. Any questions on any of that there? All right, one last one here, just for curiosity's sake here. Let's say we had this reaction here. Actually, now we'll just do aqueous. And let's say this side is red, and this side is blue. So if you have more stuff on the left there, it's red. If you have more on the right, is blue. Let's say I took the beaker that has all that in there, and I put it in a hot bath, and it turned red. I turned blue. Actually, we'll go blue. And let's say I then took the beaker and put it in a ice bath, and it turned red. Is this reaction exothermic or endothermic? Take a moment, think about it, and decide what type of reaction is this. Hot water turn blue, cold water turn red. Exo or endothermic? Exothermic, endothermic, not enough information. Was it? Endo? All right, so let's see. If I put this in a hot water bath, that's like increase in the temperature, right? And it turned blue, which meant it had to shift to the right-hand side in this case, right? And that means I basically added temperature, if you will. And when we add, it always shifts away from the side it's at, which would tell me based on the first observation, my heat should be over here on the left, right? The second one here, I put it in a ice bath, and that means that it is decreasing the temperature or removing, if you will. And it turned red, which meant it shifted to the left in this case. And when we remove something, it goes towards it, which would tell me my second observation that the heat is over here on the reactant side. By the way, they both agree, which they should, right, in this case. And because it's on the reactant side, this would be an endothermic reaction, yeah? Any questions on that there? All right, any questions on Le Chatelier's principle? That wraps up chapter 12 in the books. We're off to chapter 13. A reminder, we're quizzing on chapter 12 on Wednesday, I think is what I said. So we'll go with that. And it will cover all of chapter 12, including the Le Chatelier's principle that we talked about today. All right, so acid and bases, chapter 13 here. An acid is a couple of characteristics of it. They have a sour taste. Obviously, don't taste any acid or bases in lab, but vinegar, for example, is acetic acid, citric acid, and fruits. They react with certain metals to produce hydrogen gas in some reactions that you may be familiar with. Everybody's favorite single replacement reactions, maybe a little hydrochloric acid. This guy comes in, kicks out the hydrogen. When hydrogen gets kicked out, that is hydrogen gas that it produces, and a little zinc chloride as well. A little balancing like we're in chemistry class here. That is a single replacement type reaction. A reminder, right, that the guy coming in, like the zinc in this case, needs to be more reactive than the hydrogen for this reaction to take place. If it's not, it will not take place. They do react with carbonates and bicarbonates to produce carbon dioxide and water. So if you have maybe a little hydrochloric acid plus some sodium carbonate here. This is, unlike the top one, a double displacement reaction. Yeah. Two positive guys going to switch partners, going to make a little H2CO3 and a little sodium chloride in this case. A little bit of a 2 there, a little bit of a 2 there. And as you may also remember, perhaps the carbonic acid here will quickly go through a decomposition reaction and make CO2 and water. Yeah. So that very quickly breaks apart and makes CO2 and water. Bases, on the other hand, they feel very slippery. Many soaps are bases, things like drain cleaner, those are all bases. A lot of our strong bases come from group 1 or 2 on the periodic table. Also a reminder just to make sure everybody's on the same page, especially with nomenclature when we talk about acids and naming. Right, acids, the cation for all acids is H plus. It is the positive part of it. And when we go to name acids, it really does involve whether or not there is oxygen. So if there is no oxygen involved in that acid, the name is hydro something ic acid, HCl. There is no oxygen in that. And this is hydrochloric acid. cation is H plus, anion is Cl minus in this case, right? The missing part is from the anion part of the name. If you have something like HBr, again, no oxygen there, so hydrobromic acid. Again, H plus and Br minus is our ions that are involved here. By the way, acids typically have the AQ symbol next to it, which is the aqueous symbol. It means it's a solution, and that is why we call it hydrochloric acid and not hydrogen chloride, which is a gas. Yeah, so when you take hydrogen chloride gas, you bubble it through some water, you get an acid, which is hydrochloric acid, HCl. Now, if it does have oxygen, it will contain everybody's favorite thing, a polyatomic ion would most likely be in there. And if it does contain oxygen and it is an acid, it is sometimes referred to as a oxyacid because it has oxygen in it. And if you remember, those polyatomic ions end in one of two ways, either ate or ite. And that is also really important for your acid name. So if your polyatomic ion ends in ate, the acid is something ic acid, like HNO3. NO3 is NO3 minus, H plus. That is nitrate. This is nitric acid. If you have H2SO4, SO4 is SO4 2 minus, that is sulfate. This is sulfuric acid, right? And obviously we need two H pluses to balance out the charge, right? -2 on the sulfate, +1 gives us +2 on the other side. If it does contain oxygen and your polyatomic ion ends in ite, then it is something OUS acid, like HNO2. That is NO2 minus, which is nitrite, and H plus there. And this would be nitrous acid, yeah, OUS. So if it does contain oxygen, the acid should not have hydro in the name. Hydro is only for ones that do not have oxygen. Questions on that there? That hopefully should be a refresher, I hope. All right. Now let's talk a little bit about some definitions of acids. One of the first sort of definitions of an acid is the Arrhenius definition of an acid and base. And Arrhenius said that an acid is something that can produce H plus ions in solution, or H3O plus ions in solution. So when we talk about something having the ability to be an acid, what we're really talking about is the ability of that thing to release in solution H pluses, and H pluses are what sort of makes something an acid. In the case of acid-base chemistry, if you see H plus, which is the hydrogen ion, also, by the way, also called a proton, and that is again because hydrogen has one proton, one electron, and no neutrons. And the way you become positively charged is you lose an electron, which leaves it just a proton, right, left over. And H3O plus, which is a polyatomic ion, and that is the hydronium ion. They are, for all intents purposes, the same thing in acid-base chemistry. So you can use H plus, you can use H3O plus. I'll be honest with you personally, I use H plus a lot of the times, or most of the time. Nowadays, books like to use H3O plus. So anywhere I write H plus, you could pretty much swap it out for H3O plus. That goes in equations for the most part, and also formulas as well. So in formulas, people use H3O plus versus H plus. It basically means the acid part of the solution. So that's basically what it means. And that's what we see here. This is really hydrochloric acid dissolving in water. to make basically hydrochloric acid. Because it's a strong acid, this guy is going to react with water. What it's essentially going to do is it's going to shuttle over there an H plus over to water, and that's going to make our hydronium ion and chloride. And this is really, again, just some hydrochloric acid in water, basically, and it is how it naturally is in a solution. You could just as easily for this reaction write it like this, that hydrochloric acid dissociates into H plus and Cl minus. So these are really equivalent equations. The only difference is in the bottom line, I didn't use water, so I didn't get H3O plus. I got H plus versus H3O plus. So if you want to use water, which is perfectly fine, and again, nowadays books use water a lot with it, you'll just get H3O plus on the right-hand side rather than H plus. If you're not reacting that acid with anything other than it's just kind of breaking apart in water, basically, or in solution, you can show it like on the bottom and just use H plus. Again, they're equivalent to each other in this case. Now, a base is a substance that can produce hydroxide, and much like an acid, what we're talking about here is the ability to produce free OH minus ions in solution, which is hydroxide, a polyatomic ion. And here, this is actually a weak base. Ammonia is a weak base, NH3. And even though it's a weak base, it does not have hydroxide actually on it, but it can react with water to produce hydroxide. And when it's in solution, it will actually grab an H plus off of the water. And the result of that is it's able to produce free OH minus in solution, and it makes it a base. It is a weak base, as we'll talk a little bit more about in this chapter. As you can see, we have our equilibrium type of arrows, our reversible reaction that's occurring in that situation. Most strong bases, as I mentioned a second ago, come from group 1 or group 2 on the periodic table and have hydroxide right on board. And something like sodium hydroxide will break apart 100% because it is a strong electrolyte into sodium ions and hydroxide ions in solution. So if you had a solution of sodium hydroxide, that's pretty much all you have in that solution. You have none of these guys still together. And that's why something like sodium hydroxide is a strong base, because all it has to do is go for a swim and it's going to produce a lot of hydroxide really quickly in that solution. The ammonia here is more of a weaker base because it's got to go find some water, do a little reaction to produce that hydroxide. And because it's a weak electrolyte, it's not going to produce as much free hydroxide in that solution as you will get from just sodium hydroxide basically falling apart. Group 1 and group 2 on the periodic table, right? Group 1, I believe they still call that the alkali metals. Been a while since I taught that class. Not really. Group 2 is the alkaline earth metals. Yes. The word alkaline means basic, basically, here. So a lot of our strong bases come from group 1 and group 2 on the periodic table that have hydroxide in it. If you go where lithium is, lithium, sodium, potassium, hang a right-hand turn there at calcium, strontium, barium. You put any of those guys with hydroxide, pretty much a strong base is what you're going to get in that case. Obviously, up there on top there, our hydrochloric acid is a strong acid, which is why it has a one-way arrow, right? Nobody coming back the other way. Everybody's completely breaking apart because it's a strong electrolyte and going to break apart. And that's why something like hydrochloric acid is a strong acid, because much like our base there, all it has to do is go for a swim and it's going to release that hydrogen really easily. And it's going to produce a lot of free H plus in that solution. And that's, again, why it's going to be more of a stronger acid. And say something we talked about vinegar a second ago, which is acetic acid. And that right there is acetic acid. And this is a weak acid, and it's only going to release like that hydrogen, not as much as like HCl. It's going to basically stay together and release a little bit of that H plus in the solution. So there are weak acids and strong acids, and there are weak bases and strong bases. The difference again between them is if it's a strong acid or base, they're going to be able to release either H plus or OH minus super easy, and it's just going to produce a lot of it really quickly in that solution. And if something's more of a weak acid or weak base, it's not going to release as much H plus or OH minus as a strong acid or base would. Any questions on that there? Yeah. for the acid. If you say it one more time, if you do not use the H2O here, if you do this, yeah, if you were going to write the reaction for this, um, that's what it should look like. The water would be excluded. Now, I would say for the acids, a lot of people will exclude the water and do it like the second way. But for the bases, it's a good idea, perhaps, especially if it's a weak base, to leave the water in. Because a lot of times you'll be able to maybe understand what you're going to get on the other side. It just kind of helps you sometimes. So definitely for the bases, not really strong bases, but weak bases, people will definitely leave the water kind of in there. It kind of helps you visualize maybe what you'll get on the product side and where the hydroxide is actually coming from. Now, this was a really good sort of definition for a acid and base, but it was pretty limiting in the sense that what Arrhenius did was a lot of work with just strong bases that had hydroxide in them. As we just saw and just talked about, ammonia, for example, is a weak base. So a more general definition of an acid and base is one that was brought to us by Bronsted and Lowry. And the Bronsted and Lowry definition of an acid and base is an acid is a proton donor, so that is an H plus being given away. And a Bronsted and Lowry base is a proton acceptor, so that is an H plus being accepted. And it's really important to remember that it is not just the hydrogen. And that's sometimes people kind of focus on the hydrogen part of it, but that plus part of it is important because it does change the sign of whatever gains it or loses it, right? If you lose a positive charge, do you become more positive or more negative? You do become one more negative, right? Because basically you're losing a proton in this situation, right? So now you have more electrons than protons, right? So you become more negative. And if you gain that positive charge, which is a proton essentially, you will then have more protons than electrons and become one more positive. So the sign does change as you either accept the H plus and give away the H plus. And again, that's something people sometimes very commonly miss. Sort of a consequence of the Bronsted-Lowry definition is it will actually create partners on the other side of the arrows. So for example, in this situation, the ammonia is our base, which means it's going to accept the H plus from our water. So in this case, it is the water that's going to send the H plus over to the ammonia. When it does so, that NH3 now becomes, as you can see here, and it was what we were just talking about, NH4 plus. So it gained the hydrogen and it went from a neutral charge to a +1 charge because it gained the positive charge there from the hydrogen. The water will lose an hydrogen, which leaves it an oxygen and a hydrogen, and it was neutral to start with. So when it loses the positive charge, it becomes hydroxide over here, OH minus. So again, that's a really important aspect of it. Now, there are things that are related to each other. So this guy here and this guy are related to each other. They look similar. And this guy here and this guy over here are also related to each other. And the relationship is what is known as conjugate acid bases pairs. So the base over here, its partner on the other side is what is known as the conjugate acid. And the acid on the left-hand side, its partner on the other side is the conjugate base. Now, what is the only difference between like the acid and the conjugate base or the base and the conjugate acid? The absolutely only difference you could have is that difference right there. It is 1 H plus difference. 1 H plus difference is the only difference there can be between those two things for those things to be related to each other in this aspect. As you can see, as you go from the base to the conjugate acid, because the base accepted the H plus, it has one more H plus than it started with. And as you go from the acid to the conjugate base, because it gave away the H plus, it has one less H plus than it started with. You always find when you look at an equation, your regular old run-of-the-mill acid and bases on the left-hand side, the reactant side, and your conjugate partners on the product side. Yeah, so that is where you find each of these things when you look at it. Any questions on that? Now, by the way, the acid one that we talked about earlier with the hydrochloric acid, we could again write it with the water present. We'll get H3O plus and Cl minus. And again, in this situation, we're going to actually get the H plus transferring in this direction. And this is our acid. This is our base. And on this other side here, this guy and this guy are related to each other. That's going to be our conjugate base. And this guy and this guy relate to each other. That's going to be our conjugate acid. It is still a one-way street, even though there are partners and pairs here that are related to each other. It also brings up an interesting thing that you sometimes do see, and the idea here is this. In the case above here, our water was a acid. In the case on the bottom, our water is actually the base in this case. And there are certain substances that can actually act as either an acid or a base, depending on the situation. And those things are what are known as being amphoteric. So if you have a amphoteric substance, that is something that can act as an acid or a base. And water is an example of that. In certain situations, it can act as an acid. And in certain situations, it can act as a base and will accept the H plus. It is actually, as we'll talk about, what happens when water is with water. In one case, one water acts as an acid, the other water acts as a base, and they're constantly doing that reaction in like a glass of water, if you will. That's constantly sort of happening. Any questions on that there? So clearly the H plus or the H3O plus, which is the same thing, are the OH minus. Again, is the amount you have of each of those, what kind of determines, as we'll talk about, is it going to be an acidic solution or a basic solution that's going to happen. All right, so why don't you take a moment here. Which of the following can be a conjugate acid-base pair? So for each of the combinations there, see if they meet the definition there, and then we'll talk about it. Is that the only difference between these two in order for these guys basically to be pairs? So we look at the first one here, we have HCl and OCl minus. Why they can't write ClO minus, I don't know. But this is a difference of an H plus, but it's also a difference of a oxygen, which means it is not a pair. Again, the only difference it could be is one H plus, nothing more. Here, if we look at H2SO4 and SO4 2 minus, the difference here is two H pluses, which means no good. That is not a pair either, even though they do come from each other, but they are not considered a conjugate acid base pair, as it could only be one H plus difference between them. H3O plus there. Oh, I skipped it. Let's do the next one. NH4 plus and NH3. The difference here is one H plus. So that is a winner there. Again, you could get that by either putting the H plus on the NH3 and you get NH4 plus, or take the H plus off of the NH4 plus and you're left with NH3. H3O plus and OH minus, the difference here is two H pluses, which means no good. And obviously we got number 3 there, which seems to be the only pair. So you may be asking, why is like H2SO4 and SO4 2 minus really not pairs? So something like HCl that we see here, this is what is known as a monoprotic acid. Monoprotic means it's got one H plus basically to give, kind of like your titration experiment where you were given either monoprotic, diprotic, or triprotic sort of acid. Something like sulfuric acid is what is known as a diprotic acid, and that has two hydrogens to give. they actually come off one at a time. They actually don't both just drop off, even though when you look at equations, sometimes it appears that way because what you're looking at is the overall equation of what's happening. What would actually happen here is the sulfuric acid would actually dump one H plus first and create HSO4 minus. Then what happens is that HSO4 minus will dump a second hydrogen off and become SO4 2 minus in this case. It is a stepwise fashion that it occurs, and that is why this guy here and this guy here, they are partners because the only difference between them is one H plus. This guy here and this guy here are also partners because there's only one H plus difference. But when you try to jump the line there and go directly from here to here, they are not partners because that is like two steps down the road, and that is why they're not related to each other. Again, by the way, you get the overall reaction by adding these together, where these guys cancel, and you get H2SO4 gives you 1 and 2 H pluses, which is maybe the reaction you mostly dealt with last semester. And it's the overall reaction of what's happening, not the stepwise dissociation. And that's what happens with diprotic acids. They do lose their hydrogens one at a time. You could also have a triprotic acid like phosphoric acid, right? It's got basically 3 hydrogens to give, right? And each one of those does come off one at a time. Is it easier to remove the first hydrogen or the second? Which one's easier? First one's much easier because after you remove the first one, you now have something with a negative charge and you want to rip off something that's positive from it, right? So it's much harder to do that electrostatic attraction, right? And when you get down, say, to the third hydrogen for phosphoric acid, it is extremely hard for that one to come off. So most of the hydrogen actually does come off in the first kind of one that comes off in a diprotic or triprotic acid, because it does get progressively harder as you continue to try to remove that. Any questions on that there? All right, we'll wrap that up for today.